Good morning, ladies and gentlemen. Today at the virtual conference FLAPS 2020, I will open the session with my presentation, ChipFilm Patch Sensor System with Integrated Readout ASIC for Biomedical Applications. The trends towards miniaturized flexible electronic system with multiple component integration has been reached to a next level in the health and medical sector. In the past, sensor systems were manufactured without intelligence. The bulky readout ASIC was before outside, and now the processing moves inside the body. This is another generation of flexible systems. An example is given here, a strain gauge sensor foil with onboard intelligence, and I will propose the following two potential applications. The first is to detect the curvature of an intracardiac catheter in vivo, to support catheter navigation during a surgery, shown as a blue tube at the image on the right upper side. The advantage is that computer tomography, which was used before as the imaging method, will be reduced to a minimum, and this will help to reduce the X-ray exposure for the patient. The second application I will propose is to detect the respiration of newborns and premature infants. Since the lung system of premature infants is still in the embryonic status, an accurate control of aerosol dosage while monitoring the abdominal respiration is highly required. The sensor system with the integrated ChipFilm patch is placed face up abdominal, and the strength of the respiration is measured, and via a feedback loop, the dosage of the medicine is triggered. In this work, the focus is on the process optimization of the ChipFilm patch and the electrical characterization of the sensor readout ASIC. The idea behind the ChipFilm patch is to integrate ultra-thin ASICs with thicknesses of less than 30 micron and several other components such as thin film batteries or flexible antennas, as shown on the photograph on the right upper side, in one polymer foil. To accomplish this goal, the polyimide PI2611 is employed because it provides excellent material properties such as the required biocompatibility, mechanical flexibility, and a low thermal expansion coefficient, which will reduce the process-induced stress during the fabrication. The ChipFilm patch can act as a stand-alone system, as shown in the image before, or as an interposer, shown here on the right side, which can be integrated in another sensor system. The wafer-based ChipFilm patch process is performed under CMOS-compatible cleanroom conditions, and the process starts with the preparation of a 150 mm silicon wafer by the gradually spin coating of polyimide on the wafer. The polymerization is finalized at 350 degrees to obtain the required material properties. The polyimide is then structured photolithographically and etched with a reactive ion etching process to form a few micrometer deep cavity. A thin layer of benzocyclobutadiene is spin coated on the polyimide, which serves as the adhesive and facilitates the chip adhesion to the polyimide. The chip was back thinned down to 30 micrometer and is placed face up in the cavity with help of a manual die bonder tool. A close-up view of the chip after the placement is shown below on the right-hand side. To reduce intrinsic stress, the chip is then covered by gradually spin coating of polyimide. Then the polyimide is structured photolithographically by using a photoresist soft mask and a laser direct writer, which provides a minimum accuracy of less than 5 micrometer. The chip pads will be opened by rear etching of polyimide, which is shown here highlighted in blue on the close-up view. The connection from chip to foil level is formed by IC co-alloy metallization and structured and dry etched afterwards. The silver colored chip to foil interconnects are shown below on the right-hand side. Due to the fact that the 30 micrometer thick chip shows a bit more warpage compared to a bulky silicon chip. Polyimide is spin coated in order to compensate this stress effect. In general, the ChipFilm Patch technology is well suited for embedding ultra-thin chips. However, it requires good knowledge of the material properties to compensate the thermal mismatch. For the external communication, the fan-out pads will be open by using a thick photoresist soft mask and polyimide re-etching process. In order to ensure the biocompatibility, the open fan-out pads, which are shown on the right below, are covered with 300 nanometer thick evaporated gold and are structured via a lift-off process. The finalized ChipFilm patch is laser cutted with a CO2 laser and released from the silicon carrier. It has a total dimension of 4 × 4 square millimeter and a maximum thickness of around 60 micrometer. I would like to address a few challenges which we are dealing with in the ChipFilm patch fabrication, namely the chip rotation after the placement, the non-uniformity profile after spin coating, and the polyimide rear etching process. But for time reasons, I will focus on the spin coating process of polyimide and photoresists, which is challenging, especially on structured substrates, which is mainly generated after the chip embedding. Since polyimide shows a different spin coating behavior due to its higher viscosity, this leads to a more surface inhomogeneity on the substrate. The coating process was then fine-tuned for each material by changing the spin speed, the acceleration, and the intermediate soft bake. Furthermore, we are able to monitor the polyimide uniformity profile above the embedded chips, which we'll discuss on the next slide. First, I will show you the uniformity profile of the spin-coated polyimide. Here the focus is on the chip as indicated with the red arrows on the schematic cross-section on the upper left side. The 3 graphs show the uniformity profile after gradually spin coating of polyimide above the chip. We have 2 things to consider. A more inhomogeneous polyimide surface on the chip edges are observed, and this will lead to an inconsistent etching profile during the opening of the small chip pads and consequently to polyimide over-etching. On the other hand, thickness deviation in the chip center tends to be more uniform with each additional applied polyimide layer above the chip. The recent findings can be transferred and integrated in future chip design, where the chip pads may be located inwards near to the chip center to avoid an over-etching. Before, I have mentioned that the polyimide rear etching process is highly dependent on process steps, such as the spin-on coating. The focus is now on the way outside the chip, as indicated with the red arrows on the schematic cross-section here on the left upper side. In general, to open the fan-out pads on the wafer level, an appropriate soft mask is required to protect underneath structures. By the adaptation of the spin parameters, such as reducing the spin speed to a minimum, and by the reduction of the acceleration, we have achieved a more uniform surface profile and furthermore a 50% increase in the photoresist thickness. The advantage of a homogeneous soft mask profile within the rear etching process is faced below. The microphotograph shows a close-up view of the open fan-out pads. The step height was measured with a tactile profilometer, and the direction is indicated here with the blue dashed line. The upper height profile represents the polyimide etching with the previously used photoresist spin coating process. only a total height of 1.2 micrometer of the fan-out pad instead of the original 5 micrometer is obtained. Compared to the graph below, the height profile shows the 5 micrometer deep fan-out pad after polyimide etching while using the optimized process. In conclusion, the optimized spin coating process will resolve the problems with the polyimide over-etching and avoid damage of the underneath sensitive structures. Now I will continue to present the sensor readout ASIC. The ASIC was fabricated at X-FAB foundry using 0.18 micrometer technology. The ASIC was back-thinned in our institute down to less than 30 micrometer by using the dicing before grinding process. For the initial testing, the ASIC was assembled in a ceramic package, shown on the photograph on the right-hand side. The signals from 6 whetstone resistor bridges will be measured through I2C communication, depicted in a simplified schematic below. The initial testing of the 30 micrometer thick ASICs shows a change from 1 ohm in the base resistance at 3.5 kilo ohm. The measurement corresponds to a voltage change of 209 microvolt at 10 bit of the analog signal-digital converter output, as indicated in the graph on the right side, where 3 output signals of 3 different channels were tested. I will present to you now the first results of the functionality test after embedding the sensor readout ASIC in the ChipFilm Patch. After the release from the silicon carrier, the ChipFilm Patch was also assembled in a ceramic package depicted here in the middle of the slide. The graph on the left side shows the signal response from one measured channel at 3.6 kilo ohm. The change in the amplitude corresponds to 206 microvolt, which is consistent to the initial test of the ASIC before the embedding. The embedded readout ASIC before shows the same functionality behavior than after the embedding in the polyimide. For the conclusion, I will briefly summarize our results. I have discussed the benefits of the ChipFilm Patch process optimization, such as the adaptation of the spin coating parameters, which has a positive effect on the polyimide rear etching. We have successfully integrated the 30 micrometer thick sensor readout ASIC in the ChipFilm Patch, which is now ready for biomedical applications. The successful functionality test of the 30 micrometer readout ASIC before and after embedding in the ChipFilm Patch shows the same signal amplitude. And in addition, we have finished already the strain gauge sensor, and we will start right now with the characterization. I would like to thank the German Bundesministerium für Bildung und Forschung for the financial support of the project FlexMarks. Furthermore, special thanks go to the members of IMS Chips and in particular of the Advanced Packaging Department. Thank you very much for your attention. If you have any question, you can contact me via email. Thank you. Goodbye.